I'm just going to introduce Dr. Findlay, who is your first speaker. Stuart Findlay is a senior aquatic engineer who works at the Cary Institute. The Cary Institute is a 25-year-old private, not-for-profit firm that does ecological studies. Dr. Findlay has been working in the Hudson Valley area on salt and other contaminants in the water. And without further ado, I'd like to bring Dr. Findlay up to tell us about the Cary Institute's work.
Okay, thank you very much, Lee. And again, thanks to everyone for coming. What you're going to hear today is that this is a very diverse problem with many angles to it. And if we don't get people in the room talking to each other that can address all those angles, we're not going to make any progress. So no one technical group is going to solve this problem. We all got to get together and work on that. So my job for today, for this morning, is to give you a sense of sort of what we know about this issue downstate. My institute and most of the information I'm going to show you is from the mid-Hudson Valley. And to make a long story short, we're sort of further down this path of a salt in the environment problem than you are here. So if you see what we've learned, what messages we're taking from that, it may help guide you to perhaps not tread quite the same path. My co-author here is Vicki Kelly. Vicki manages our long-term monitoring program at Cary, and she's been instrumental in both pulling the information together and recognizing the problem for what it is. So I'll talk about salt in Dutchess County waters, where is it, when, and sort of the so what. And I will try and draw analogies to what's going on.
Yeah, you have to use the arrows. We can just use that.
Okay, got it. So here's the take-home message. You're always supposed to start off and wrap up with the take-home message, so you're going to see this a couple times. Get ahead of your trajectory. I'm going to make the point today that there's a long-term trajectory to the way we've been applying salt in the environment. And I don't want to make it sound like it's an inevitable path to gloom and doom, but there are things that happen, and the sooner you know about it, the better off you are, and the better your chances are of taking some steps to avoid some of this. So get ahead of your trajectory, and frankly, you guys are ahead of your trajectory. Think slow. A lot of the time when we talk about this particular issue, we tend to think about the episodes and the spikes and the maxima and concentrations and things like that. Part of the tricky part about this whole issue is that things happen much more slowly than we think. The consequences take longer to emerge, and things you do to avoid those consequences, the actions you take to minimize those consequences, take longer to appear. So think slow and be a little bit patient. I'll show you examples of that. And the last one there, many environmental issues, you wind up sitting, on two sides of the room, shouting at each other that, oh, you're doing this and it's bad, and you want us to stop doing that and it's bad and it's going to cost money, or whatever the problem is. In this case, there really aren't any bad guys. I mean, everyone has a stake in this. Everyone wants to drink the water. Everyone wants to support the natural resources that are so important to the economy of this region and others. Everybody wants to be able to drive on the roads. Everybody wants the fire truck to show up at their house when it's on fire. Almost everybody wants the school buses to show up, although I understand there's a younger contingent that's not quite so excited every day. So everybody really is working towards the same thing. And as both Willie and Lee have said, how are we going to get there in discussions like that? So I'm going to try and touch on all of these as I go through it. And then I will come back to this right at the very end. Okay, so salt in the environment. Clearly, we put salt in the environment through a number of ways, and you either know already or you will see and hear that road salt is the biggest one. And it's a slippery slope, and part of the trick is it's this slow appearance of the problem. So we've been putting reasonable amounts of salt on the roads for some decades, and for quite a long time it wasn't obvious there was an issue. You put salt on the roads. Spring comes, you get high runoff, it rains, the stuff's gone, it's in the ocean, which, as I understand, is salty already, not a big issue. It's taken a while for this issue to appear, to be recognized for what it is, which I think is quite a serious problem. So the slippery slope analogy, I'm not really that wild about the slippery slope analogy, but given where we are, I thought I'd use it. The sooner you recognize that you're on this trajectory, the better chance you have of doing something about it. Now, if I got on a slope like this, on skis. The sooner I got off there, the better. If I came to anything close to terminal velocity on that thing, I'd be a dead man. All right, so the sooner you recognize the trajectory you're on, the better your chances are of doing something about it. So that's why I decided to go ahead and use this analogy. And you'll see some of this, the time lag before some of these consequences appear is kind of the tricky part here. I'm going to give you this, as Lee said, the presentation is available. So just some numbers for reference. I'm not going to go through all of these. What were background concentrations like before humans did any kind of salt distribution in the environment? Certainly less than 10 milligrams per liter. A couple lines of evidence, Dan will talk more about this. Where do you start seeing sort of environmental consequences? A variety of different things happen on the order of 50 to 100 milligrams per liter. Some of these are causative, where that concentration is actually causing some negative effect. Some are just associations. Something else is happening at the time you see chloride concentrations reach those levels. But about 100, you start thinking something's going on you might not be so happy about. There are a variety of more stringent requirements. There's a drinking water standard, secondary standard, 250 milligrams per liter. To the best of my knowledge, you guys aren't near that in any sort of sustained way. Most of the lethal effects are up to a gram per liter, 1,000 milligrams per liter. In general, I ask people to remember something a little simpler: green, yellow, red. Orders of magnitude 10, 100, 1,000. If you're at 10, life is pretty good. If you're 100, start paying attention. If you're 1,000, you got a problem. For Dutchess County, downstate, about halfway down the Hudson Valley, the average for all the samples that had been taken, a bunch of surface water, a certain number of drinking water wells, was 80. So we're right around that 100, start paying attention number. I don't believe your average here is near that yet. It'd be better if you didn't get to that, frankly. But just some sort of quantitative sense as you're looking at graphs and figures, 10, 100, 1,000. So here's Dutchess County. Tiny little button to push again. Yeah. All right, it's down there. Dutchess County, we have a big range of concentrations in Dutchess County. Much higher population density than what you have here, the Hudson River on the left. We've got about an order of magnitude range, a little more than an order of magnitude range in concentrations across various surface waters. Some of these are in the 10, so really don't worry about it. Some of them are well over 100. Again, start paying attention. And I'll talk about what's driving these patterns in a few minutes. But in the county, we recognize that we're certainly at that point where start paying attention to what's going on. For bigger picture, where are we in sort of the national scale of surface water chloride concentrations? This is a very nice paper put together by John Mulaney at USGS. Forested, agricultural, and urban samples were taken from across the Midwest, I believe. That dashed line is the chronic standard from EPA. It's about 200, 300 milligrams per liter. Urban areas, clearly higher concentration than either agricultural or forested. Not surprisingly, this is a log scale, so again, you get this 10, 100,000 reference marks over there. Dutchess County, we're in the 80 to 100 range, so that's what that yellow box is, Dutchess County. Adirondacks, from looking at Dan's data, you're somewhere around 10 on average, and Dan will talk more about episodes and things like that in a few minutes. So again, we know what land cover types are associated with higher chloride. The county where most of our work has been done, we're ahead of you if you want to look at it like that. I guess I don't really like to look at it like that. We're further down the track than you are. So you've got some time to take some action, I think, is the message from this. We talked about salt in the environment. We've talked about road de-icing. It turns out in places where budgets have been done, where people have tried to calculate for a given watershed, where is the salt in a particular stream coming from? So for the Northeast and Midwest, where these sorts of calculations have been done, most of it's from road salt. Some is from water softeners. Very little is from wastewater. People often talk about wastewater and septic systems as generating salt in the environment. They really don't that much. Road salt for the ice-covered parts of the country or the continent, that really is the bulk of what's going on. And I'm not trying to suggest that this photo is a good practice. It just happens to be the photo we've got. I reckon we're better than that. You were better than that. Okay. So, but anyway, where the budgets have been done, road salt really is the big thing. So getting a handle on road salt, doing a more effective job in treating the roads is really the answer to the question here. All right, so I'm going to show you some of the findings we've got from Dutchess County, and this is going to be the think slow part. I'm not saying think slowly, I'm saying think about things that are slow to happen. Because for this particular problem, we thought that it was a quick issue, a quick response, put salt on the road in January, rains like hell in April, the salt's gone, end of topic. It's much slower than that, and it frankly was a big surprise to most people that have worked on this sort of issue. It takes much longer to move around than we thought. And I'll show you 3 different patterns in both space and time that I hope will persuade you about this slow behavior of salt. So we'll start off with long-term changes in concentration. This is an almost 20-year record. The record has gone on. It's the little stream that's monitored that's behind our institute. Concentrations over this period went up by about 2-fold. More salt showing up in the stream. For any of you that have been to the little village, Millbrook, I know a few of you have, there are no new roads to speak of. The village engineer says they buy essentially the same amount of salt for the same road miles that they've done for years and years and years. So it's not as though they're applying more salt, and there aren't new roads. Okay. What's happening here is that the salt that was applied years ago is now starting to show up in surface waters. Okay. So there's sort of a residual effect, a slow release effect. So you're only seeing the consequences of those decades of salt application after some years. It's not like you put the salt on the road and you see it all right away. That's not what happens. It takes a while to appear. For some reason that frankly we don't understand, and you'll hear that a couple of times. So these long-term increases in concentration, I suspect it's the same here. There are not a lot of new roads. I know that people that put the salt on the road don't like to put down more than is necessary. It costs money in several different respects. So it's taking time for this issue to make its full appearance. Don't go the right way. This is a different watershed in the region. Same story, no new roads. If anything, the town is trying to minimize the application of salt to these roads, about a doubling in concentration over a 15-20 year period. Okay, so it's not just we've got some weird little stream that we sampled. This seems to be a general pattern. So you're putting the same amount in year after year, and it's taking a long time before you really see it. So here's the other strange thing. You think about salt, well, that's a winter problem, right? Again, put the salt on the road January, February, a lot of water moving around in April, stuff goes to the ocean, end of story. These are monthly mean concentrations for the stream that we monitor. And if you see a seasonal pattern there, your eyes are better than mine. They're essentially all equal. If you want to really, there it is, August, which is not the month we get the most snowfall, you might be surprised to hear, actually has the highest concentration of salt in the stream. So again, obviously the salt is applied in the winter, right? It's not showing up as concentration in the stream until summer, right? So there's something, again, holding on to that salt in the watershed, not releasing it as quickly as it's applied, not letting it leave the system as quickly as we might have thought. From a biological point of view, summer is when many of the sensitive stages of organisms are present, the young stages, the reproductive stages. So this is a time when you're actually worried about high concentrations. It may be that high concentrations in February, things are in resting stages, they're overwintering in some form or another, not as sensitive, but in summer they certainly are. So having high concentrations in summer is an issue from a sort of biological response point of view. So here's a spatial pattern. I talked about Dutchess County before. The population gradient is from the northeast to the southwest, for those of you that have been down through the Hudson Valley. The cities of Poughkeepsie, Fishkill, Beacon are close to the Hudson, sort of in the lower left corner of the map. So the population gradient, therefore the road gradient, density of road gradient, is from the upper right to the lower left of that map. So if you sample, we've done this at a couple different streams. This is for Fishkill Creek. If you sample from the headwaters, which are on the right-hand side of the graph, the headwaters, down to the mouth, you get about a 4, maybe 5-fold change in concentrations as you go downstream in that system. Now, if this were in January, February, I don't think anybody would be the least bit surprised. There are more roads in the southeast, southwest corner of the county. You're tracking a road gradient as you go down the headwaters. We know we put salt on the roads. If this were a pattern that you saw in January and February, no one would be the least bit surprised. That's exactly what you expect. These data and others were collected, I believe this is July. We've done this several times. You see it consistently. So these patterns are showing up in summer. So the salt that's being applied is not leaving quickly. It's still there generating these spatial patterns and concentration in summer. It's a slower problem than we thought. And again, just to drive home the point that it's road density, it's people density that's causing this. This is again for the Fishkill Basin. In the summer, this is for a bunch of sub-watersheds, and it's the percent residential land cover in those watersheds and the concentration of chloride in the waters and the little streams that drain those watersheds. So again, places with 30, 35, 40% residential land cover have higher chloride than sub-basins with a few percent residential land cover. This were January, February, no one would be the least bit shocked. Maybe they wouldn't be worried. But they certainly wouldn't be shocked. The fact that this shows up in summer is what's so odd about it. Again, a slower problem than we had, than I at least had anticipated. We've done some modeling. We being other folks. These are some folks from Syracuse University, engineers from Syracuse University. And so they constructed a model. If you know how much salt is being applied, what the soils are like, what the water budget is like, you can generate, if you put this amount of salt around the watershed, how much should show up in your stream. And I'm really going to try and get this thing to work. There we go. And so the green line is the base case. So this is across time. Here's the chloride concentration. This is again for the Fishkill Creek. The green line is the base case. And what they did with their model, what it's mostly used for, is playing scenario games. So they have a scenario where they reduced road salt application by half, and they had a scenario where they doubled the amount of road salt being applied. This is per lane mile, per road mile. So when you reduce the road salt application by half, that's the red line down here, the concentration does go down, but it only goes down by 20%. If this were a quick response problem, the concentration should go down by 50%, and it didn't. All right. So you have put less salt on the road. It's going to take more than a single year for the benefits of that to show up in this scenario. Turns out to be exactly the same story. My children would say technologically incompetent, which may be true. But, so the green line here is this, you get the same message looking the other way. If you double the amount of salt you see in the stream goes up, but only by 34%. Should go up by 100%. All right, so again, slow response. You're either putting more on, putting less on, but it takes a long time to see the benefits. So the two messages from this are, you haven't seen the worst of your problem yet, so you think this year, our concentrations are blank, or whatever they happen to be. You haven't seen that wave of salt come out of the system yet. Right? It takes time for that to happen. You haven't seen it yet. So you haven't seen the consequences of your past actions yet. The flip side of the coin is if you take action to cut back your road salt, it's going to take a while for that to show up. You're not going to see results instantly. You may see some results instantly, but be patient, because it may take a while before you really see the real gain from this. That's what this slow response to this problem is telling us. So both the temporal trends, the trends through time, and the trends across space that I showed you suggest there's slow flushing of this salt from the watershed. It's not like put it on January, gone in April, problem's over. Where is this stuff staying? I don't know. If anybody knows, come tell me, because I'd kind of like to know. There are several good possibilities that we've looked at, and there's some evidence for several of these things. We just don't know. It could be sitting in shallow groundwater. It could be stuck to soil. There are probably some other things that could be going on. All right. So we don't know how it's staying around. We're pretty clear that it is staying around. So when we talk about science this afternoon in the breakout, I would propose this might be worth tossing around a little bit. Something's holding on to salt. So I'll talk quickly about an example of what are the consequences of this slow behavior. It has consequences for how you manage and how quickly you expect to see benefits or costs, for that matter, of your management actions. It's going to take a while to see either pluses or minuses, gains or losses in concentration. But it's got effects on biology as well. And Dan may speak about this a little bit, or we can talk about it later. There have been a variety of sort of tests done on what sort of concentrations are effective. But this is a case where a local high school student came and worked with us for a winter and was interested in looking at the acute, so these rapid fluctuations in concentrations, and the effects of that on stream algae. These are tiles that came from the stream, and we let algae grow on them, expose them to different salt levels, versus chronic. Okay, and again, we've tended to think about the salt problem as an acute problem, where spikes and the maximum concentrations are what's really driving the problem, as opposed to, again, the slow response. What's the average concentration? What are the concentrations that they're exposed to for days and weeks, as opposed to hours? So the acute versus chronic effects. So this is the question that Lauren set out to address. The record here, the dots there, are the chloride concentrations, again, in the small stream that we monitor continually. And you see spikes. You see spikes in January and February. And I haven't done it. I'll bet you if you go back and look at the weather records, that's probably when it's snowing, or freezing rain, which frankly I think is worse. So you do see these spikes. They don't last very long. Those spikes, those are the acute exposures, the quick exposures. High concentrations don't last very long, as opposed to the background level. And again, for this stream, we're on the order of 50 milligrams per liter. So what Lauren's experiment did is she exposed these tiles that had algae from this stream. She exposed them to both an acute treatment, which was 500 milligrams per liter. That was the maximum. She did different concentrations. 500 milligrams per liter for 4 hours, and that's based on the record here, versus a chronic, where her highest concentration was much lower, only 100 milligrams per liter, but it was for a month. Okay? And both of these treatments, both of these experimental manipulations are well within the realm of reality for what's happening with surface water concentrations in our part of the state, at least. So what happened? So this is the acute treatment, the results of the acute treatment. So again, much higher concentration, up to 500. No statistical difference in the abundance of algae on these tiles as measured by the amount of chlorophyll that was present. So the spikes in concentration did not have an effect on the amount of algae that were growing during her measurements. Okay. In contrast, the chronic exposure, the lower concentration but lasts longer, had a 30% reduction in the amount of algae growing on these tiles. So this I think is a nicely done piece of work by Lauren. It's done one time in one particular situation, but it does point out that, again, the slow behavior of this issue, slow behavior of chloride in the environment, can be as big a deal as the response of the environment, be it organisms or some other process, to these acute effects, these spiky type consequences that you see, the behavior of chloride in the environment. So again, think slow. Okay? It's not as fast a problem as we had believed probably 20 years ago. Okay. The fact that, we've got this slow behavior, again, early action, and that's where you guys are. You're in the position to take early action. You're not as far down this slope as many other places. Early action, much easier. So I want to just wrap up talking with what in many people's view would be sort of the ultimate end point to this. What are we drinking? We drink water. And everybody wants to have good water to drink. This is a map of drinking water wells in Dutchess County that were sampled. You get this very strange distribution of points because the county level stuff was semi-random, and so they're distributed all around the county. One particular town put in place a requirement that when a residence is sold, you have to test the well, and those data become public. And I'll let you guess which town it was that did that. It's East Fishkill. And so most of the points in the analysis I'm going to talk about today is from the high density of points in East Fishkill. So it's not representative of the county, but the findings, I think, are still relevant. So the good news part of this, there is a good news part to this issue, that in Dutchess County, 90% of the wells are below this EPA secondary standard for drinking water. So 90% of the people are drinking good water from a chloride point of view. It's more than 90% because many of them are on public water supplies. But for the private wells, 90% of the wells are good. Okay, 10% are not. And what you worry about is, do the people that have that 10%, do they know they're not? That's the problem. All right, but good news, 90% are below that limit. The sodium standard is actually more strict. And that sodium standard is for people that are on really salt-restricted diets. Only 40% are drinking good water. Okay, and I hope that other 60%, at least the fraction of those 60% that are supposed to be on low-sodium diets, know about it. All right, many I suspect do not. Okay, so this lets us look at chloride in drinking waters, and no surprise, the density of roads around a well is an important predictor of whether or not that well has high concentrations or not. So I'll try one more time. On the left-hand side, so across the bottom here, this is the area of pavement within a 3,000-foot circle around each individual private drinking water well. If you're down in the 10 to, let's say, maybe 15 acres within that circle around the well, chloride concentrations are pretty low, 20, 30, maybe 40. When you get out to places where you have 20 to 30 to maybe 50 acres of paved surface in that circle around the well, concentrations can be over 100. Okay. So again, the implication is that having a high density of roads around your drinking water well is not good. All right. And it's almost certainly because of the road salt issue. And so the question, I think it was either Lee or Willie asked the question of, can this stuff penetrate to aquifers that are tapped for drinking water? And yes, they certainly can. How long it took for this to happen, I'm not sure we can say. Again, I think you guys are probably ahead of this curve. I'm hoping you're back here on the left side somewhere. Okay, and I'll just wrap up by pointing out that this whole road salt thing, it's serious. It costs money. Bad decisions can cause harm to the environment. Bad decisions can cause unsafe roads. Bad decisions are never good decisions, right? What is, as I say, engaging about this problem is that everybody understands it. If I started talking about the, oxidation reduction of perchloroethylene and the effect of sulfate complexation on that, everybody goes, what the hell? I couldn't care less. All right, but everybody understands salt, and they know they don't want to be drinking it. They know it's bad for freshwater organisms and processes. They know we put it on our roads because we want to be able to, have their kids go off to school so you get some peace and quiet in the fall. So everybody understands what the problem is. So it's an engaging problem. It's a good way to get people talking to each other. At this point in time, it's not a terribly threatening problem. If someone goes out and pours gasoline in somebody else's well, you're going to have lawsuit, you're going to have law enforcement, you're going to have huge issues right away. All right, so it's a very, gasoline contamination of drinking water is a very threatening problem. At this point, road salt is not. I hope we don't get there, but at this point it's not a threatening problem. It's easier to talk about. All right. Point sources aren't always the problem. I won't say they're never the problem, but they aren't always the problem. All right, and because it's not a point source, everybody's to blame. You know, we all drove here. I'll bet you everybody drove somewhere last February. It's everybody's problem, right? So there should not be a lot of finger pointing about, oh, you're the bad guy, you caused this, you fix it. It's everybody's problem. And it's everybody's gain. It's everybody's benefit. And the last thing I'll say, I didn't get into this, but for Dutchess County, where we see high chloride, we tend to see high other things. And nitrate, again, it's not a terrible issue in drinking water. It does have some negative environmental consequences. But we do see it associated with chloride. So chloride could be sort of like the camel's nose in the tent. It's the first part of the problem you see. There may be other things coming. All right, so again, get ahead of your chloride and you may get ahead of some other issues as well. So with that, I'm going to stop. So I tried to persuade you that, you know, there is a trajectory. You know, I think downstate we're further along than you are. There are other parts of the country that are way further down this slope than we are, so way further than you are. Think slow. Think about the slow aspects of the problem. And again, this idea that anytime there's some sort of environmental issue, there's some finger pointing back and forth. It just kind of seems sort of unavoidable. But there isn't a good guy, bad guy side to this problem as far as I'm concerned. So with that, I'm going to stop and I'll take the question. I don't know who's doing the timekeeping. I guess I'll leave it.
We have a few minutes for questions for Dr. Findlay, if anybody would like to ask.
A quick question. Have you looked at salt marshes and things like that? This is in references. I understood you said that the biotic things were hampered by salt, whatever algae or whatever it is. But there must be something in salt marshes in places like that that is adopted and will kind of eat the salt. Is that a possibility?
Yes. So there are many things that live in the ocean or live in salt marsh. They're perfectly well adapted to living with salt. Our blood is essentially the same concentration as salt water. So we're salty creatures ourselves. Most of the stuff in fresh water, again, the younger organisms, larval amphibians are particularly susceptible to this. They're not used to salt, right? So small amounts make a difference to them. There are other organisms that need way more salt than we're talking about here. So yeah, life is diverse, and some things like salt, some things don't. What you have in the lake out there doesn't like salt.
I'm wondering, in that graph that you showed a spike in August, if there's any way to take into account evaporation.
So that's a good question. So I talked about concentration. And what's happening in August is the stream is fed by base flow. All right, so it's obviously not snow melt. It tends to be sort of dry time of year for us. So it's that shallow groundwater that's maintaining the flow of the stream even when it doesn't rain. So the fact that we see that concentration, even at low flow, says that concentration has to be in the groundwater. Okay. Now the fact of the matter is that things in that stream, whether it's groundwater or surface water, that's a concentration they're living with. And again, that's the reproductive time, that's when those sensitive stages are present. So you can't necessarily evaporate that much water to give you that concentration. You're changing the source of water. And it tells you that other source, that base flow generation, that shallow groundwater, has that salt in it. So again, we're going to talk, when we talk about the science issues, where should you be looking for this, I'm going to call it the mystery salt, although I don't really mean that, but where should you be looking for it?
I have to leave earlier than I expected, so I'm going to just bring this up now. I know we're talking about more of the science issues and the environmental impact, but I've always been considering the economic impact, and I didn't know if you had done any studies. As a driver, and many of us who live out in McCollum and drive to Saranac Lake, have had more car work done than I've ever had to do. And Years ago, I remember I had a brand new car and I rarely had to replace the muffler, the brakes, or any of this. And so the question would be, has anybody done an economic study with mechanics and car dealers, number one, and then how much has that cost us in repaving, resurfacing roads, and what was the third one?
Bridges is the other thing. So the highway superintendent's here, the town
But
supervisor.
the environmental impact, I think sometimes, we're all very interested in it, but very many people, the level of disconnect they have when they're in their vehicle and the environment that they're passing through, it's well, it's personal, private well. There's a disconnect, and so I thought, how much economic impact on the things that people have direct use of, if it was applied, you're paying out of pocket this amount of money due to the salt on the roads, would that have a different impact on the way people approach this?
Yeah, so again, the highway superintendents and the town supervisors can talk about the extra maintenance, rusting out of vehicles, bridges.
So I'm not
and
just
everything.
talking about highway, I'm talking about personal.
Yeah, so there have been.
Like Mark Calderon, having a survey at his mechanic shop.
There have been national studies on the cost of corrosion using road salt. The numbers are huge. I'm not going to pretend to remember what the numbers are, but the numbers are huge. So again, I don't like the win-win analogy either.
Right.
But cutting back on that aspect of it would have a fairly quick and direct economic benefit to individuals that they could see that, that muffler's lasting 10 years.
Sure.
Stuart, I thank you, but we're going to have to move on.